So good morning, good afternoon, good evening, everyone. Welcome to the EPS-SG Scatterometer User Preparation webinar. EPS-SG, the European Polar System second generation, is EUMETSAT's next generation polar orbiting satellites, and the scatterometer is on board the EPS-SG B satellite. We also have the next generation geostationary program, MTG, the EUMETSAT third generation. Both these programs offer they offer continuity from the current missions, as well as they provide new capabilities. So we consider it very important to support our users in the preparation towards an early uptake of this data, as well as to make the best use of this data. This is why we are organizing this user preparation webinars from a very early stage of our user preparation activities. So these satellites will be launched. The first of the MTG satellite will be launched in late 2022. And from there on, we will have a string of satellite launches. And we thought this is the right time to start such a series. And this is the third one in our user preparation webinar series. And we plan to do, we had an MTG lightning imaging mission webinar in February. We had a hyperspectral infrared webinar, infrared sound webinar, which is on board both MTG and EPS-SG in October 2020. We have an optical imaging webinar coming up in June, and also a 3MI webinar coming up in June, and several others on the microwave coming up towards the end of this year. So we're trying to cover all observation missions in MTG and EPS-SG this year. And so you have to stay tuned to EUMETSAT external webpage, where we announce all these webinars in due course. So today, the focus is on EPS-SG scatterometer. And I'm happy to see we have about 70 participants so far. I hope more will join, because we had more registrations actually. So this is quite exciting times. So today, like I said, the focus is on scatterometer, and our first session, we will focus on the scatterometer instrument itself, how it makes measurements, what are the improvements of the current method SCAT, the level 1D processing, basics of data format and dissemination. And the second session will focus on the soil moisture product development and the applications. And tomorrow we will have the first session on the wind products. It's the same time. We start at the same time tomorrow. We will have the wind products and the sea ice products. So today, the session will start in a few minutes, but before that, I would like to remind you that for asking questions, you have to use the Slido tool, slido.com, and enter the event code SCA there. So if you look now in your chat, you will see that you have this information presented there. And you can ask your questions there. You can type in your questions. You can also upvote the questions if you like some of the questions and you want an answer. And we try to answer all the questions today, if possible. And if not, they will be taken up offline, and you will be provided all the questions and answers separately after the event. And also, use the Zoom chat only if you have any technical problems, like if you find any technical issues, you can post it there. We will try to help you as much as possible. And yeah, like I said before, we make the recordings, and this will also be made available to you. With this, I would like to hand over to Stephanie Lino, who is presenting the first talk today. Stephanie, over to you.
Thank you, Srilke. So I will just start to give you a bit of an introduction to the EPS-SG scatterometer. And so yes, we already had a bit of background on the missions. The scatterometer is basically part of the mandatory programs that EUMETSAT has. which are the METEOSAT and METEOSAT third generation, also the EUMETSAT polar system and the follow-on mission. And I'm not going to dwell much on this overview here, but go into the details. So the scatterometer missions, which EUMETSAT has, are currently METOP, ASCAT, which are flying since 2006. Actually, we have at the moment 3 operational scatterometers in orbit, but METOP A will leave the orbit at the end of this year. So the replacement systems for that are already being built, and for the EPS-SG, for this EPS second generation, we will have basically satellite A and satellite B series, and the scatterometer will be on the B series, and you can see the planned launch dates. So we have a number of different instruments on the EPS-SG satellites. So the A series has more or less all the optical missions. So TRIM I, MWS, Sentinel-5, METEMAGE, and ERZNG. And the satellite B series will have more the microwave missions. For instance, MWI, ICI, and SCA. There will be radio occultation instruments on both satellite series. Of course, the scatterometers that EUMETSAT is flying are not on their own. So they are part of an international constellation, virtual constellation of scatterometers. So you can see in this table we have a number of active scatterometers at the moment, with much more to come. ASCAT and SCA are operating in C-band. We have a number of Ku-band instruments which are operating and also are in preparation. And we also have some quite interesting missions coming up, which are combining C and Ku-band and have things like rotating fan beam instruments and so on. So those are going to be some interesting times in the future for scatterometry. So, and yeah, SCA will be part of it, and I'm going to say a bit more about the instrument and the processing now. So SCA will inherit a lot of good things from ASCAT. So the first generation ASCAT is a C-band radar. It's an active instrument. It's a fan beam scatterometer, so it has 3 fixed antennas looking to each side of the swath. So that makes 6 beams. We have a swath width of 550 kilometers and covering an incidence angle range, as you see on the slide. And ASCAT is only operating in NVV polarization, so it transmits vertical and receives vertical. So for SCA, we made some updates of that. So we will slightly change the frequency, have a wider swath and a wider incidence angle range, and we will add horizontal polarization and cross-pol on the mid-beams. This is done mainly to improve the wind retrieval in high wind conditions. So on the right-hand side here, you can see a bit of the the basic layout of the system. This is just a picture of the instrument itself, how it's basically built into the satellite. So this is an image that's coming from the manufacturer, Airbus. And on the right hand side, you can actually see the one of the test antennas. And just to give you an impression what the thing looks like. What we do in terms of processing, so we get the level 0 the unprocessed data from the instrument, and then we are processing this at EUMETSAT into level 1A, which basically includes radiometric and spectral corrections and calculation of calibration factors. And we basically analyze the telemetry. Those are internal products to EUMETSAT, and they are not provided to the users. They're just for internal use. What goes out to the users is then the level 1B. So we have two different level 1B products. So the first one is the full resolution called SZS. Those data files will contain radiometrically calibrated backscattering coefficients, which are geolocated basically on their original range location across the swath. And of course, the product will contain quality flags. The next product we are generating is the resampled product. This basically collects the individual measurements from the individual beams and resamples them on a swath grid. And this will also include quality flags, of course. This data then goes to the SAS, in this case the OC SAS and the H SAS, and then is processed into level 2 and level 3 products: soil moisture, ocean vector, winds, and sea ice parameters. You will hear more of that later today for the soil moisture, and then tomorrow for the winds and the sea ice. Just a bit of technical background. So we are basically, as I said, this is an active instrument. It sends out chirp pulses and then receives the return echo, and then translates this into backscatter measurements. And because we have a bit more complicated measurement sequence than on ASCAT, I thought I'd just make a bit of an animation on that. Sorry. So you have a certain sequence of measurements. This is basically half a shot cycle here, and so you have all those measurements overlapping, and then you basically, for the gridded product, you are collecting them on the individual grid points, and then you get something we call pentaplets. So you have 5 measurements per grid cell. So the 4 mid and aft beams plus the cross pole and the HH measurements. So we are combining the cross pole. For the calibration and validation we will do for the SCA instrument, we will follow basically the plan we have developed for SCAT instruments. So basically, before launch, we are developing a plan for the calibration and validation, and to have a look at the instrument characterization, and checking everything in the ground segment. So that's the pre-launch phase. And as we go into commissioning, we will check that everything on the instrument is working, and we'll verify the calibration and validate the products. And then after about 6 months of commissioning phase, we will enter basically routine operations, and then we'll monitor the product in the long term and also improve as we see necessary. Then I'm now giving you a bit of an overview of how we are going to do the calibration validation. So we have two basic approaches. So one is the validation using natural targets. This can be used to assess the long-term stability. And then we are using active transponders as absolute reference of our measurements. So natural targets. Here we are making use of properties of scattering properties of natural targets, which have a near constant backscatter over a long time. This allows us to assess the long-term stability of one or even more instruments, and also to check that the calibration between the beams is stable and so on. And this allows us to see if there are any jumps in the signal which occur. And there are several well-established methods to do that. So mainly we will focus on the rainforest and on the ocean. This is just to give you an idea what the backscatter will look like. So this is an example from EUMETSAT. So for SCA, there are 2 channels missing. What you can see is essentially that the ocean is very dynamic, and you can see if you are looking at Brazil that it looks very, very boring. So there's not much backscatter at all. Not much. There's a high backscatter, but not much structure to the signal, and that's actually for us it's a good thing. But back to the ocean. As I said, it's very dynamic. So what we can do from the ocean signal is basically to check the intercalibration of the beams. So because what you're actually doing for the wind retrieval is you are looking at directional surface roughness, and you have an 180 degree ambiguity in the signal, and for the ocean validation you're actually making use of that property. So you are looking at long-term statistics, and in this way you can examine the interbeam calibration. So as I said, if you look at the tropical rainforest, it's very, very boring. But this is a good thing, because you have isotropic backscatter from the forest canopy, and this is in all polarizations. And what we are doing to validate the signal is to also generate long-term backscatter statistics. And in this way, we can see jumps in the calibration and cross-check the calibration of the different antennas. And it's actually quite accurate and quite good. And we are going to use it for SCA as well, because it's well established. The thing with the natural targets, though, is that the underlying assumption is that you have a signal which doesn't change, which you can never tell for natural targets. So it's not really it's not really clear. If you see a change, does it come from changes in the surface or changes in the observable, or does it come from anything on the instrument? So for the rainforest, it's so on the right-hand side in the plot, you can see basically a tree cover change for the Amazon rainforest area. So I think we are still lucky, but you can see the changes creeping in from the sides. So we need to be very careful with that. So it's not it's a good reference, but still So for this reason, we have an absolute calibration, which is based on using active transponders. We have 3 of those transponder instruments on different sites in Turkey. And for ESCAT, we are switching into a dedicated calibration mode, and then we are measuring a signal of a very well-defined strength, and then as we repeat the passes over those transponder sites, you can basically sample the antenna gain pattern, and in this way you can basically generate an antenna gain pattern, and then you can use this to correct in the processing. For SCA, we will do something very similar. So the issue with the ESCAT transponder calibration is that you are doing this by switching into a dedicated calibration mode, so you have a gap in the data. This is no longer the case for SCA, because we will not do this in the echo window, but we will receive the signals in the noise window. So we will basically measure, the transponders will wait until the satellite passes, and then repeat back the signal after a certain delay, so it ends up not in the echo window, but in the noise window. So we will not have any gaps in the data during the calibration, which is good because we can then do this more continuously. So I'm actually already at the end of the first part of my talk. So just to give you a summary, so we have EPS-SG SCA, which will ensure the continuity of the EUMETSAT scatterometer missions for quite a long time period, more than 30 years. And we are building on the strong heritage from the SCA instrument. So from the instrument, from the processing, and also on the calibration. And we will improve the high winds retrieval capabilities by adding cross-pole channels and have a better coverage and a higher spatial resolution. So that ends my talk, the first part of it. If you have questions, please ask them. Thank you.
Thank you, Stephanie. Actually, if you have any questions, you can put them in the Slido now. There is, I think you can see the Slido. You can go to slido.com, type in SCA there, then you can see it. Yeah, there is a message in the chat exactly how to do it. But in the meantime, we have a couple of questions there, and I will share them now. 1 minute. Yes. Okay, Stephanie, we have a few questions there, and
Okay.
if you can see them, but I can also read them out for everyone. I think we'll take the first question. What are the pros and cons of using C-band versus Q-band for scatterometry?
C-band has been found to be less sensitive to rain effects. So that's the main point, I think. So you have for KU band, you always have to include for corrections or flagging for strong rain events. This is not necessary for C-band.
Okay, we move to the next one. What is the minimum and maximum? Oh, I can't see it. 1 minute, guys. Can you read it out? Because
okay, so what is the minimum and maximum wind speed that SCA will be able to reliably detect.
Ah, yeah, okay.
If I could keep any numbers in my head reliably. So at the moment, ASCAT is saturating at 25, around 20 to 25-ish meters per second. This is for the VV, and this is no longer the case if you include cross-pull channels. I think it doesn't saturate as much, but we will need to validate and to see essentially when the data is there.
Up to 40, can it? I don't know. I have read somewhere that it can detect up to 40.
Yes, I have this number in my head, but you need to study it and validate the retrieval, and then this is where it gets complicated. I think Ad can give you more numbers on that.
And it's really not in today. He has a CGMS talk at the same time. So, but yes, I think this question we can keep for tomorrow, because
I think you will get all the answers to that and very much details from Ad.
Yeah, I think maybe this question we can still keep if the person who asked the question, if you can come back tomorrow or maybe late. I mean, if you're not free tomorrow, we will provide the answers anyway, because that's quite an interesting question, also related to the minimum wind speed that one can detect. Yes. So then next,
I think there's not really much change on the minimum.
Okay.
But the interesting bit is actually the saturation and high winds.
Yeah. So the maximum is what is going to matter with the new scatterometer, the new SCA.
Yeah. What is the latency of the distribution of the level 1B products? For ASCAT, the user needs to order the files for downloading. Thomas, I'm going to answer this in my second talk. I do have a second part where I'm going to say something about the distribution and the files and so on. So this will be answered in a couple of minutes.
There is one more. How dense is the transponder network? How many is efficient for a proper calibration?
So at the moment we are using 3 transponders, and this will stay like this. So you just need to be able to sample the gain pattern at an appropriate density, but we are doing this by repeat measurements. So you don't need a very dense network of transponders, and also those things are quite complicated because you have to make sure the signal is very well calibrated. So we have 3 of them. That's enough.
Just an add-on question. At the moment, when you do this for ASCAT, how often is that done? Maybe you mentioned it, but do you do it for every overpass or over the transponders, or?
In theory, we should have a calibration campaign regularly, which then for us ASCAT will take 1 or 2 months.
Okay.
And then determine an update to the gain pattern, and then keep it running for a year or so or 2.
Okay.
And then do this in regular intervals. I mean, the thing is that you need to balance between the gaps in the data and the calibration you're doing. So and ASCAT is very stable, so you don't have to do this very often. So it's a bit of a balance, because each time you pass the transponders, you create a gap in the data. At the moment, for SCA, we will do this a bit more continuously. And the thing is, we at the moment we are installing new transponders. So we have a lot of gaps in the data because we are doing testing, but the calibration campaign will follow. Hopefully, let's keep our fingers crossed by the end of this year. The next one. So it's the answer to that is a bit more complicated then.
Okay.
What is the size of the level 1B SZF footprint? I will come back to this in the next talk.
And there is another. The impact of rainfall on radar backscattering.
Okay, I don't have any slide ready on that. I can dig it out and get back to you on that.
Yeah, we can answer it offline then. Yeah.
Yes, we can answer that one offline.
If you have that ready, then I mean that's good enough. Yeah, we can do that later. So
yeah,
these are the questions that I see. Oh, there is one from Christina. Yeah. Hey. Thanks, Stephanie. I was wondering if the SCA soil moisture product will be delivered with a climatology like the ASCAD soil moisture product is currently. Will you use ASCAD past data to build this climatology until enough SCA data is accumulated? I think this is for the next talk, or can you answer already?
Oh yes, this is an interesting question. Actually, is a good point, and maybe Wolfgang can answer that more easily than I can do that.
Yeah.
So I'm referring that one to Wolfgang.
Christina, we have after this next talk of Stephanie, then we are moving actually to the soil moisture.
But I can directly react.
Thanks, Wolfgang.
So I think we keep initially the two products separate, but if the cross calibration is very good, as I would expect, it would be holding us nothing from making a joint climatology. Condition is that we start combining ERA spectrometer, method ASCAD, and second generation SCA into the joint joint data record.
Okay, maybe this is an add-on question to that. So when you during the commissioning, you will compare the you will have a validation of the current. I mean, you will have a validation between the current ASCAD and the new SCA level. I mean,
and it's not going to be just happening at the commissioning phase. It's going to happen through the mission.
But during the commissioning, you will have a validation. You will have to produce a Okay, so for the reliability of the product. There is one question actually: how the other agencies doing how the other agencies doing regarding advancements in the SCAT measurements globally, which are comparable missions to EPS-SG?
Yeah, this is basically going back to the beginning of my talk where I showed all the different missions internationally. So there is an Indian mission which has KU-band. There are quite a large number of upcoming Chinese missions, spectrometer-wise, and they do actually have quite a number of interesting instruments. So there is a combined KU-band mission, and there is something called EUMETSAT, which is basically combining rotating beams with the fan beam, so the rotating fan beam instrument. So things are moving and will get very interesting in the near future. Also, there are a number of the Chinese missions which have inclined and drifting orbits, so we will see a lot of interesting developments in this regard.
There's actually a comment in the chat box. It says that the Chinese HY2D satellite was launched yesterday, successfully launched yesterday. Good. So there's scatterometer there, right? The scat, yeah. What you mentioned earlier. So yeah, congratulations.
Congratulations.
And yes, good news. There is also, I think that was the impact of rainfall. This question, when will the SCA data be available? I think the launch is currently scheduled, this onboard METOP SGB, and the launch is scheduled beginning early 2025 now, and the data will be available 6 months later, as Stephanie mentioned.
Yeah.
Okay. I think if I don't see any more questions, but we can maybe take a 2-minute leg break, and then we come back in 2 minutes and Stephanie can proceed with the second talk.
Okay.
2 minutes.
Okay. Thank you.
Regina?
Welcome back to the shorter. This is just an overview of the data product. So we've already seen this slide here. So the interesting parts here are data we are going to deliver. So that's to the users. So that's the 1B products. And then for the SAF products, the level 2 and the level 3, soil moisture, ocean winds, and sea ice. I'm going to just focus on the level 1B because that's what we are basically distributing, and I will leave everything else to Wolfgang, Art, and Steiner. So this is to answer your question. So this is a comparison of the data products. So you can see the SCA products in comparison to the heritage ASCAT products. So for SCA we have the gridded products. So currently for ASCAT we have the operational SZO and the SZO products, which have 25 and 12.5 kilometer grid spacing. For SCA, we will double the grid spacing and the resolution. In terms of KP, we will be in the same region as for the SZO, and also for the calibration accuracy. The SZF is basically the product where the individual measurements are in their original footprint geometry, so they are not co-registered on a grid. And here we have basically a footprint size of about 5 by 25 kilometers. The file formats will be NetCDF and buffer for SCA products. So it will be a bit more simple compared to the current ASCAT native formats. So this is just to give you an impression of the structure of the products. You have the full information on the products under the link I've put in the slides. So it's available through the EUMETSAT website. As I said, data will be available in NetCDF format, so it's more or less self-explanatory. So this is basically for the full resolution product, the structure here, and this is what the gridded product will look like. But again, the full documentation is available. What we also have available is test data. At the moment, we have a first version available of the test data, so it's basically an initial version to just for the users to familiarize themselves with the product formats. We have selected one full orbit, which contains essentially synthetic backscatter, so which means constant backscatter and some noise. So we didn't simulate any geophysical signals. The data set is available through the EUMETSAT website. So we will update this in the near future. We are currently working on that. This will contain 3 full orbits of test data and cover a range of various nominal and non-nominal processing scenarios. This is basically to test the operational processing, and also maybe for the downstream processing chains. It's interesting. Data dissemination and timeliness. That was the other question. So we have both global and the regional data stream, basically. At the moment, the plan is to disseminate the gridded product via EUMETCAST over in BufferNet CDF format. We are expecting some updates on that, so discussions are ongoing. And the full resolution data will go to KNMI for the WINS processing. And everything will go into the archive, so it can be downloaded from the archive. Currently, we are not planning any dissemination on the GTS for SCA level 1B data, because we don't really see any demand for that. But if there is any, then I will be happy to hear from it, so I can maybe change it. Timeliness for ASCAT A, we have currently 2 hours 15 minutes, for B 90 minutes, and for EOS, which is similar to the regional processing, we have 15 to 30 minutes. For SCA, the global data processing, we have a target of 70 minutes, and for the regional processing, it's 30 minutes. I think to note, yes, I think I already said that the regional data processing for SCA will be a bit similar to the current EOS, but I think it's not identical in terms of stations, but the information is available. And finally, data is available through a different number of channels in EUMETSAT. So we have the archive and EUMETCAST, and there are quite a number of updates to the data provision at EUMETSAT. So it's worth having a look. And this is actually, that's it from my side already for this part of my talk. Thank you. So if you have questions, please let me know.
Just sharing. I think that's the question that is highlighted here, Stephanie. Can you explain the difference between spacing and resolution of level 1 products?
So we have a difference between spacing and resolution because the grid spacing is twice the resolution of the products. So the grid spacing is higher than the actual resolution of the products. And as Art can tell you, this is to avoid to avoid running into trouble when resampling the products. So it's basically to make use of to oversample it in order to make use of the full data
solution. I think there was one question related to the latency before. Maybe that question can
that was from
maybe that
Thomas,
you answered that. Yeah, I think you answered that already. Right? No, I was just referring to this comment. For a SCAT, the user needs to order the files for downloading. This is from the archive, actually.
That's from the archive, but this is for users who don't have access to EUMETSAT.
Yeah, if you do not have near real-time access, then
yeah.
So you do not have to. Depends on which access mechanism you use. Stephanie, in one
as I said, there are quite a number of changes to the entire archiving system and data access system at EUMETSAT at the moment. So things are very fluid. Fluid at the moment.
In one of the earliest slides, I think for SCA, you said you have NetCDF buffer and native. So so that's the current, what you call the native format for ASCII. You continue that for the SCA regime as well, or?
Essentially, the native product format for SCA is NetCDF.
Okay. So there's no. It's not. I mean, I just
misunderstood. No dedicated native file format any longer. So it will just go be formatted in NetCDF by default for all EPS-SG machines.
Yeah. Okay. So okay.
So this is standard.
I think this is a question. What's the size of the level 1B SSDF footprint?
That was what was it, 5 by 25 kilometer.
Okay, that's a pixel size. Okay.
That's actually footprint geometry.
Yeah. SSDF footprint. I just wanted to make a comment because you showed the EUMET, the different channels. In the EUMET view, you can actually, if you carefully choose your times, you can actually, the ASCAT wins you can actually see the ASCAT wins there. It's quite a useful tool. Yes, in EUMET view, you can see that.
That's new that they did it. Yeah.
Yeah, so you can actually put your METOP A, B, C ASCAT wins there. So it's quite useful and interesting to look at. I think that's all the questions now. What do you have?
Okay. Good.
Let's wait for a minute if anyone has. Okay. Hi, everyone. That's all the questions we got for Stephanie today, but you can also pop your questions when you feel like. We will answer them offline if they come up. The other thing I want to mention is that we have also a short poll running in Slido. This is to generally get some get some impression about how the presentations are going today. So we'll have one poll for today and one poll for tomorrow, where you can express your opinion about how this webinar is done. It's on a general terms. You can see how the level of these presentations. So I would appreciate if you can put in that there is a link in the chat box on how to do it. So it's exactly in the same slido.com. You have to go to the polls, and if you enter the, go to slido.com, enter the code SCA, and then you can see a polls option there. And if you can spend about 5 minutes there after today's session, that would be really helpful. And then also tomorrow. If you have any, I mean, there is nothing more, then we wait for 5 minutes, take a break, and then come back to the next session, which is on the level 2 soil moisture products and its applications. Thank you.
So good afternoon. Well, first of all, thank you for EUMETSAT for the invitation, for organizing this webinar. The MEDTOP second generation SCA mission will be, in my view, an extremely interesting instrument. And I think it deserves to be used a lot to understand those, to process the land surface and the cryosphere. So in my talk I talk about the land surface, and also touch in particular soil moisture product, which is the current operational soil product for the land. I'm coming from the Department of Geodesy and Geoinformation from the Technische Universität Wien. I'm a professor here since already 20 years, and our focus has been working with active microclimate sensing techniques for the study of hydrological processes. So what are the land surface variables that are affecting spectrometer measurements? So in general, we can state that microwave measurements are sensitive to the geometric structure and the dielectric properties of the land surface. And if you look at the geometric structure, we can distinguish effects like the roughness of the soil surface, the structure and the biomass of the vegetation. Of course, buildings and infrastructure is also very important, as it can have a very strong impact on scattering mechanisms. And if the land cover is, if the land is covered by snow, it's the grain size of the snow and the layering of the snow layer. And when we talk about dielectric properties, the point is that the water molecules have a permanent dipole moment. As you see here, there's a general separation of the charges within the molecule that creates a permanent dipole moment. And when now an external electric field is applied, the water molecules try to arrange themselves, so they start moving. Now, this mechanism is then causing so-called orientational polarization. And as long as the water molecules can follow the applied electromagnetic field, the dielectric constant of the material is extremely high. So if you look here to the right, this graphic showing the dielectric properties of water at microwave frequencies from about 1 gigahertz to 10 gigahertz here and up to 100 gigahertz. In particular, here at the low microwave frequencies, you see that the real part of the dielectric constant is extremely large. Only when you then come, say, to microwave frequencies in the order of 13, 14, 15 gigahertz, this is where the relaxation frequency is taking place. Basically, the molecules cannot follow the applied electromagnetic field any longer, and the dielectric constant rapidly decreases along the line. In this plot, you're not just seeing the real part of the dielectric constant, you also see the imaginary part of the dielectric constant, which is telling you how absorptive the water is. And here we have pure water, and here you would have saline water. So the frequency of the spectrometer is here at around 5.4 gigahertz in the same way as the Sentinel. And you see here we are still at the point where there's a very drastic change, while a very high dielectric constant values. So anywhere where water is being mixed into material, like if it's now for the soil, or if it's now the water within the vegetation, or if it's the water within the snow layer, you have a very, very strong and drastic effect on the backscattering characteristics. And of course, this is very interesting because for this reason, we can do a main target quantities over land are the soil moisture content. A very exciting recent product is then a rainfall product derived from the soil moisture time series. A second very important product is free thawing. This comes from the fact if the soil freezes, its dielectric properties are comparable to the one of a dry soil because the water molecules cannot move any longer. So actually we can also nicely see frozen soils with the spectrometer measurements. Of course, also vegetation has an impact, and there we can focus on different variables. For example, on the vegetation optical depth, we can look into vegetation phenology and others. So here's the sequence of spectrometers we have been working with. So starting from the spectrometer on the ERS-1 and ERS-2 satellites, over to the METOP ASCAT, and now to the METOP second generation SCA instrument. It's very nice to see how the spatial resolution has improved from 50 kilometers now to about 12.5 kilometers for SCA. Also very importantly, the daily global coverage has improved, in particular from ERS to ASCAT, but now again a stepwise improvement in the SCA instrument. And from like a microphone sensing point of view, very nicely that we now have also the HH polarization and the VH polarization on SCA instrument. This, for example, over land is extremely important information because, for example, we know that for the grassland areas, the HH signal will be even more sensitive to the soil moisture content compared to the VV. And we know that VH is going to be more sensitive to things like vegetation and other volume scattering mechanisms. So there is a lot of additional information in those data. Here you have the launch dates and the coverage and how long the missions have lasted so far. So we are in an extremely fortunate situation right now because we have 3 spectrometers in place in orbit right now. So we have METOP R that was launched in 2006, METOP B that was launched 2012, and METOP C 2018. Unfortunately, METOP R will have to be deorbited by the end of the year. So we're going to look forward to the launch of the first SCA instrument. What for the land is also very important is that we have a coverage together with Sentinel-1 satellites, Sentinel-1A and 1B, that essentially is doing the same geophysical measurements, with the big exception that the spatial resolution and the temporal coverage is vastly different. Yeah, while ASCAT has like a coarse spatial resolution, the resolution of Sentinel-SAR is very high, 20 meters. On the other side, the temporal sampling of ASCAT is unmatched and much coarser with the Sentinel-1 satellite series. So repeat coverage for the ASCAT is about daily, and for Sentinel-1 for Europe, it's about 3 days to 6 days, and globally from about 6 to 14 days. But together, these 5 satellites give very nice C-band coverage of the land surface. We've only recently started working with the full resolution data from ASCAT, so with the SFZ products. You see here data resampled now on a 6.5 to 5 kilometer grid using data from METOP R. And you see here like a swath going over mid-Europe. So what you see is that urban areas clearly stand out in the backscatter measurements. And you also see that there's a strong dependency on the incidence angle. So going from near to the far range, we have a decrease in the backscatter amplitude. And you compare those measurements from the spectrometer on the ASCAT with the ones from the SAR of Sentinel-1 on the left side. So again, we see all the urban areas, we would see water areas that are affecting the measurements. Here's the daily global coverage we have achieved with 2 METOP ASCAT instruments. Here's like one image we generated using METOP R and METOP E. Unfortunately, there's still some areas not being covered, particularly around the equator. This is because of the phasing of the two satellites with respect to each other. Actually, if there would be a different phasing in orbit, we could achieve full daily global coverage. But because of priorities that are put on different instruments, we have, as a spectrometry group, not been able to influence the choice of EUMETSAT to change this. I would hope that sooner or later this prioritization can be changed so that we get, with two instruments, fully daily coverage of the land surface. Here you see time series, and again, another very important point from the spectrometers. They are extremely well calibrated instruments, and by having several of those instruments in space, we can closely monitor if there's drifts or differences in the backscatter values. Here, this is just like one grid point over the land surface where we see impacts of soil moisture and vegetation on the data. But if we do a moving average over the measurements, we see, for example, that we have captured here a period where there was a bit of a difference between the METOP A and the METOP B satellites, which later then decreased again. But very clearly, we are able to pick up those slight differences, and if you later then do a reprocessing, we can correct them, so that we would be here now in the period where we have METOP A, B, and C, and you see how nicely the three instruments match with each other, and that the bias, the differences are extremely small. And that's also, of course, from a land application, very important, because we are now able to compare, for example, this year's measurements immediately with all the years since 2007, which is a very important advantage compared, for example, to many land surface models that have more problems of having such very clear and stable signals. You have already seen that graphics from Stephanie. So we have here this particular measurement geometry, as was already there for METOP ASCAT. Again, the improvement for SCA will be that the near range will move a bit closer. So we will start about 20-degree incidence angle for the mid beam rather than 25 for ASCAT. And we will go up to here for the fore and aft beam over to 65 degrees. So we will cover a very large swath on both sides of the satellite track. And we will have the HH and VH information, but not only for the mid beam, not for the fore and the aft beam. Obviously, this is a compromise in order to not even increase the size of the instrument and make it even more energy hungry as it already is. So how does a typical backscatter signal over land surfaces look like with incidence angle? So we see here, if we have here a particular point over the land surface, we typically backscatter decreases with incidence angle. So coming here from near range to the far range of the swath. And if soil moisture changes, typically backscatter goes up along the whole swath. If vegetation is changing, say over a progression of a year, we have the same soil moisture conditions, we see that the backscatter values increase in particular and at the far range, so at higher incidence angles, while they remain roughly constant here, say at the 20 degrees, there's less influence of the vegetation, or it can even be that the increase of vegetation leads to a decrease of backscatter here. So we can formulate this as in a model that takes into account changes of soil moisture and vegetation. So you would have, for example, here dry soil, and if there's like vegetation growing on the dry soil, we would have an increase of backscatter here in the far range, and even like a decrease in near range. And here for the wet soil conditions, an increase in the far range and a stronger decrease at nearer ranges. Yeah, and this dynamics you need to build into your model to describe it. and just showing you how this looks for real ASCAT measurements. So on top you see just many measurements of ASCAT from the 3 beams thrown into a diagram of backscatter versus incidence angle. Here's a location for the tropical forest. Here's a location for a grassland agricultural area. And here an area where it's dominated by background, a very low vegetation cover. So for the tropical forest, we see that's behaving almost like a perfect volume scatterer. And yeah, and if you would represent the data now as gamma rather than sigma 0, we would achieve a flat line. If you go to the background and low vegetation, that must have been a point where actually there's also very little soil moisture variation. So the signal is overall stable, but as you see here, there's still some quite variations. So it's more unstable than, for example, compared to the tropical forest. And the amplitude of the measurements become highest if you go into this grassland type of environments. You can have there changes in backscatter in the order of 6, 8, 10 dB, also over land. And of course, you can now separate this high variability in backscatter for the different seasons. If, for example, would look at the winter data, here the spring data, here the summer data. So you here clearly see how there's like soil moisture variation causing this variability, but the low presence of vegetation is causing a rather strong decrease. With spring, we see an enhancement of backscatter, in particular at high incidence angles. And here, this is most pronounced than if you go into the summer. Now, it's also very useful, and there's a particular makes it outstanding compared, for example, to synthetic aperture radar instruments, that we have multiple backscatter measurements at almost the same time. So we have measurements, for example, here from the mid beam and for the aft and fore beam. So we can estimate for each of these backscatter triplets the local slope behavior. Yeah, so you would see here 3 of those backscatter triplets. And if we then throw those local slope estimates into another diagram that plots the local slope versus the local incidence angle, we see it follows a certain behavior. We typically describe this behavior here as a linear model. That basically that means that if you go back to backscatter, it would be a model with a second dependency, a second order polynomial. The problem is a bit because the measurements are not very far away from each other. So the difference between mid-beam, incidence angle of mid-beam and incidence angle of fore and aft beam are not very far from each other. Noises that are within the backscatter measurements are being expressed here in the local slope values. So that's why there's a certain uncertainty in the overall slope estimates. And if we make then plots over time, we see that there's a certain range of the data, but still we could use certain like windows or smoothers that we move over the data. And this comes then still very close to a real observable. So we do minimal modeling to the data, but it basically makes that on top of having sigma 0, we also have like slope and curvature measurements from the instrument. With ERS, the ERS spectrometer, when I was a bit skeptical if this is a useful data set. Well, we used it for doing vegetation correction, but I wasn't quite sure how stable it is. And when we finally had METOP R and METOP B data, it was really great to see when we then started comparing slope estimates from METOP R and METOP B derived independently. We saw that these measurements are extremely reproducible. So we gained a big trust in the way how the instrument is characterizing the incidence angle behavior. So here in this plot, you see from 3 different locations on the Earth, you see the slope and the curvature, and you see the green lines on for METOP R and the red-orange lines are for METOP B. Yeah, in this location here, location A is from the Canadian prairies. You have in winter rather stable slope. So this is basically reflecting that there's dormant vegetation. Sometimes there's snow there, but it's typically dry snow, doesn't affect as much. And then when the springtime comes, there's a strong increase in the slope, basically meaning that the backscatter curve goes up and there's strong vegetation development in late spring and summer, and that's repeated every year. If you go to the tropical forest, overall the slope is very, very stable, so no change. And also again, very nice to see how mid-top R and mid-top B overlaps. Yeah, and the last point here shows you a place in the Australian desert. So overall, we have very stable backscatter behavior, but here we essentially have a strong rainfall event there that is then causing a rapid vegetation development. Also, these kind of things are being picked up by the instrument. So what we've started to look into was this behavior of the slope and the curvature. I mean, what you already saw from this discussion, that vegetation biomass plays an important role on how the temporal evolution of the slope is. But we also found that there's like some deviations or wobbles in the slope time series that cannot be explained by biomass. And then we started looking into, okay, what kind of other effects might we be seeing? And one effect, the particular effect, was we saw that, for example, in Austria in spring around April, we often found a local peak of the slope, which later then went back down and going up. And we were really puzzled and initially understanding what it is. We then we made an algorithm to detect those local peaks and where they occurred. And when we did this, and this is like with the black lines, the small lines here, these are those areas we detected this spring peak. And when we then compared this to a land cover map, we saw that it occurs in particular in areas with deciduous tree coverage. And then we also looked into phenology, and basically we concluded what we are seeing is that during winter time, the trees, don't have leaves. And before leaf out, there's lots of water being pumped into the canopy. And this additional water already in the canopy leads to an extremely enhanced backscatter in those bare elements. So this would then relate here to the peak in the slope. And then once the leaves are coming, the signals from the trees and stem below are already attenuated, dampening down that signal. And only the signal then goes later up when the leaves covering more area and the biomass is significantly increasing. So that means vegetation phenology, vegetation structure can have a very important impact on the slope. We also observed that we see things like drought events in slope and curvature values. Here's an example work by Susan Steele-Doom from TU Delft. So here's an area, grassland areas in the Nebraska Sandhills in the US. This is like the typical slope behavior over the year. Here would be curvature, here's backscatter, and here's soil moisture. And here we have for the years 2007 to 2016. We always see the anomalies compared to those climatological values. And when we look at the backscatter values, we see here the droughts in 2012 and 2013 very well reflected in the backscatter data. And of course, in our soil moisture estimates thereafter. But very interestingly to note is that those drought events have also a clearly visible impact on the slope and the curvature. So we now recognize that these are data that contain lots of information, but we're still trying to work out to fully understand what is happening, what is causing that particular features of the slope and the curvature. And once you have the slope and the curvature fully characterized, you can normalize the data, the backscatter measurements, to make them comparable. So your original backscatter measurements over land are difficult to work with because we can plot them here in a diagram. So measurements from the forebeam, midbeam, and aftbeam with the different colors. And obviously, there's lots of variability in the measurements, not just caused by soil moisture and vegetation, but also because we work at different incidence angles. So once we have corrected and, for example, do a normalization of the data to 40 degrees, we see we get nice backscatter time series to directly compare the measurements. And from those kind of data, we can also now do more simplified models for retrieving soil moisture. So soil moisture is being retrieved from the spectrometer data with all different kind of models. Typically would be model formulations where you use semi-empirical models like the cloud model and semi-empirical or empirical backscatter models using iterative optimization techniques. People also have increasingly been using machine learning techniques for going from the backscatter data to soil moisture retrieval. And within the EPS-SG, for the official soil moisture product, we use change detection techniques that, however, take into account the vegetation development. Yeah, so here would be a scheme of our retrieval algorithm where we would have the backscatter time series, and then using the information from the slope, we take into account that during summer the vegetation is higher and the variability of backscatter is lower, so that the dynamic range of backscatter during summer is lower than it is in winter. And yeah, these are then essentially our soil moisture retrievals. So here was one of the first animations we did. This was still work being done by Sultan Batalis, who is now with the European Space Agency. So we see how the ASCAT instrument flies over the Earth in the orbit, and then producing with the two swath the soil moisture coverage. So we have here measurements from 2012 in June. So we don't have so much problems with frozen soil conditions, even though at the very high northern latitudes we should have masked them because there's snow and froze and all ice that is not being masked here. We also have not masked for the tropical forest, which you should normally do, because obviously if it's a very dense forest, you cannot see to the ground. But essentially within our products, we do retrievals and then we provide masking layers so that the users can apply it where they think it is necessary. So there's now a couple of soil moisture data products that are being provided from the EPS-SG and further down the stream services. So we have the surface soil moisture data provided in near real time at 6.5 kilometer grid. This is for the 5 kilometer, 25 kilometer grids. Along with those near real-time data that come in swath geometry, we have data records that are for all the points on the Earth, so on a fixed Earth grid. For Europe, we also are doing a disaggregated product at 500 meter sampling to simplify the life of users that are interested with higher resolutions, and the data also assimilated into the ESMWF model. Further down the line, there's from the Copernicus Global Land, we have a soil water index product in soil moisture content in the root zone rather than the measurements just on the top of the soil. So this problem is solved with the soil water index. And within the Copernicus, we also start combining the ASCAT data with surface soil moisture retrievals from the Sentinel-1 to go to a 1 kilometer data product. Yeah, and also last but not least to mention that within the ESA Climate Change Initiative and the Copernicus Climate Change Service, we combine all the ASCAT measurement, all the spectrometer measurements to produce long data record, and we combine them with soil moisture data from different passive microwave remote sensing instruments to create the most comprehensive satellite-based soil moisture data records at a coarse spatial resolution. So in this case, 0.25 degrees. One product that is becoming operationally within the next year, as I already said, it's like a very exciting development. That this is a rainfall data product that is derived from the soil moisture data. Normally, people always think the other way around, so that they take precipitation and then try to model the soil moisture content. So essentially, this is turning the procedure around. You have a hydrological model of the land surface, and you try to estimate the precipitation from the change in soil moisture over time. So the Luca Brocca, who invented that method, calls it the bottom-up approach, because in this approach, you essentially regard the soil to be a natural rain gauge. And the big advantage from this is, for example, you have one ASCAD measurement on day 1 and then a second measurement on day 3. You compare the soil moisture retrievals from those 2 days, and essentially the method is sensitive to the total precipitation volume within the 3 days. Obviously, 3 days can be a very long time, and you may miss many important precipitation events. So the method itself becomes significantly better if you have several satellites in orbit, so that if you have method A, B, and C, that the retrievals with the so-called SM2Rain method are significantly better than just using one satellite. And you see here a comparison of rainfall data estimated from ASCAD for 4 different locations on the Earth and compared with ground-based observations. This data set is available on Zenodo, so everybody who would like to have a look at the data can download and have a careful look. Here you see an animation of the data from 2019, so this is a daily precipitation estimates. What I'm fascinated from a remote sensing point of view is when I look into the errors of the rainfall data product, it essentially directly reflects the errors we do in our soil moisture retrievals. So any improvement we can do on the soil moisture retrievals will have a direct impact on the quality of those rainfall estimates. Yeah, one product which is kind of a semi-operational product. It's included in the Copernicus soil water index data product, but not as a product per se, but just a data field, is the free thaw status. In the Copernicus product, we only do a simple, not a simple, but a change detection algorithm. One can also use more complex procedures, like we did in this publication here, where we used a combination of KU-band and C-band spectrometer data to derive the surface state flag probability. So we estimated the probability of having frozen soil conditions, non-frozen soil conditions, and thawing conditions. So like a wet snow coverage or open water on the ground. And here you have some examples. You have backscatter time series from ASCAD. This is the lila color, then sea winds, the black. Here you have the diurnal differences from sea winds, and here would have temperature data. So you see how that algorithm would convert the 2 backscatter time series into estimates of the frozen probability, non-frozen probability, and thawing probability. So very nicely seen, for example, here that we first have like a frozen probability, then we see a certain thawing signal, and then we are quite certain, okay, that the soil has thawed. Obviously, a challenge with these kind of variables is that it can be highly dynamic. There could be significant changes from within a few hours. So again, temporal coverage, temporal sampling is extremely important to make those good products. Then people also have been working on estimating vegetation. we essentially started from our soil moisture retrieval and using a water cloud model to estimate the vegetation optical depth. Overall, our idea was in making a vegetation optical depth product is to say, well, the more vegetation there is, the less variability I will see in the backscatter measurements. So I compare the variability, the observed variability of backscatter over a certain area and compare it with the expected backscatter variability for bare soil. And this is then the basis for doing an estimate of the vegetation optical depth. So the weakness of this approach is that it assumes that a lot of the signals we're getting is just from like vegetation biomass, but as we understand nowadays, it's also partly dependent on vegetation structure. So there's still like uncertainties in this data product. Maybe one outlook to the SCA instrument. As I said, the big novelty will be that we're going to have HH and VH data there. The added benefit of having VH data can already be seen with the Sentinel-1 satellite because it has VV and VH acquisitions over land. Here we see time series for different crops. So we would have, for example, here a daily precipitation and backscatter over barley, in summer barley, winter barley, weeds. And we see the upper lines are from different fields in VV polarization, and the lower lines are from the VH polarization. Yeah, so if you look at the time series, we see that obviously precipitation has an impact both on the VV and the VH. And if we then compute the ratio of VH divided by VV, we take out a lot of those soil moisture signals from the data. And what we then get is a much higher sensitivity to the vegetation state. Yeah, so there's a certain, a good relationship to, say, the vegetation optical depth. There's also a relationship to the vegetation water content. But we still need to see how in detail those relationships look like. But in any case, looking forward to the SCA, we know that we will be able to exploit much more information about the vegetation using the three polarizations. So that brings me to my last slide. So even though the instrument was designed for the winds monitoring, and I think much of the user community is still from the oceans, I think the land and also the cryospheric applications deserve much more attention because it's really a very nice instrument. So we have now already operational data products. As I mentioned, the soil moisture is an operational data product. Rainfall is upcoming soon within the HSAF. We have free thawing, part of the Copernicus land service, but it could also become an operational data product. And there's research going on to have things like vegetation content, snow properties. Didn't go into this, but if you go into desert areas, or very arid environments, we also see the scattering from underlying rocks in the data. And key applications, I didn't touch them, are numeric weather prediction, drought monitoring, rainfall estimation, flood risk monitoring, and etc. Yeah, and with this, I would like to just point to the paper by Art Stoffelen and the SCA science team that wrote up in the paper the interesting science question that we can expect for SCA, and would like to thank you for your attention. Thank you very much.
Thanks, Wolfgang. Very interesting presentation. Like you said, the instrument was designed for monitoring winds, but then you ended up with some nice products. And I can vouch that if I look at some of the user queries that we receive at EUMETSAT help desk, a lot of them are on soil moisture products. So I know that it's quite well used. Yeah, quite interesting also about the vegetation phenology was quite new to me. Very interesting to hear that. In the meantime, if anyone has any questions, you can put them again in Slido and we will take them up one by one, and Wolfgang will be pleased to answer them, I hope. Just one question from my side while others are typing their questions about the vegetation optical depth product. But, I mean, this is not yet operational, but where do you see the application of this product actually?
I think the real information content is on the vegetation water content. So we would need to understand. So vegetation optical depth is a model quantity that comes from radiative transfer theory. It's not something we can observe on the ground, but it's a modeling quantity. And the real variable of interest is the vegetation water content. And if we can sort out those relationships, it would be a new kind of data set for describing vegetation that cannot be provided by optical data. I mean, the one disadvantage of the spectrometer says over land is the core spatial resolution. That doesn't matter so much for soil moisture, but for vegetation, obviously people much like are used to 20 meters, 100 meters, 1 kilometer data. So why should we go to like 25 kilometers? And water content could be a strong motivation for doing so.
So you're still suspicious that it will not be useful in the SCA context?
I'm not suspicious. I'm just a scientist who says, well, we need to do additional research. I'm sure when we have the next webinar, or maybe 10 years, we could say, well, we get a good breakthrough with the SCA, and we are now looking for the third generation of instruments. So what do we need to improve in the design of the instrument to improve the vegetation water content product? If you would have asked me 10 years ago if I think there's going to be an operational rainfall product, I would have said no way. But it is there now.
This is the SM2 rain product.
SM2 rain,
also, one more question. Why about this, when you normalize, do you normalize it to 40 degrees? Did you say any reason for that? Or
yeah, the reason was when because it's in the middle of this walk, so you minimize interpolation errors. That's the only reason.
I think Stefan is probably having some trouble to approve the question. Oh no, this is a question. How did you manage to produce a 6.5 kilometer image? What is difference between, I suppose, standard 25 kilometers? So how did you go to 6.5?
Yeah, the image was generated by my colleague Sebastian Hahn. We introduced a new global Fibonacci grid, and we essentially did a boxcar filter, as was recommended by Art Stoffelen, because he had very good experience on the coastal areas with that new window. And when you compare it with the coarse resolution data product, you've seen it to the very right. Obviously, the differences are most pronounced in areas where there's fast change in the backscatter properties. So, for example, going from an agricultural land to an urban area, or going from a coastal land area to the ocean, there we will see very, very strong differences between the 25 kilometer product and the one sampled at 6.25 kilometer. Well, again, don't confuse the sampling with the spatial resolution. So the spatial resolution will still be coarser than 6.25 kilometer. So we still need to look into this. I think the effective resolution is maybe something in the order of 10 to 15 kilometer.
I think, okay, that question is answered, Stefan. I think. Yeah. For additional information on vegetation status, have you considered using high resolution optical imagery, S2, Landsat, or BRDF derived from MISR type data?
Well, we have not considered yet the Landsat or Sentinel-2 type of data, but of course we've been working with MODIS, MERIS, Sentinel-3 type of vegetation data products. And we're doing different experiments that actually, by also including them in the retrievals, we can further improve the vegetation correction in our retrievals. So overall, we are currently looking into starting and using a much more complex radiative transfer theory model compared to the change detection algorithms in our retrievals. That also kind of trying to parse for SCA the additional information we have there. Things look very promising. On the other side, I also have to say that our past algorithm is very useful because it's very robust. So we will do some more science to make sure that also the more advanced radiative transfer algorithms that may then also ingest optical data for doing retrieval are as robust as the current approaches.
Okay. There's another question from Christina.
Yeah.
Thank you. And the freeze-thaw product sounds very interesting because it seems that would help us make better use of the observations in terms of quality control. Would this product ever be used to flag the soil moisture product more dynamically?
Yeah, we've essentially used that product within the Copernicus Global Lens Service to flag the data there. It's not part of the HSAF. This doesn't sound logical. It's for historic reasons. What we are trying to work on is that we start combining the ASCAD data and SCA data with near real-time weather data to have improved flagging of freezing conditions and snow. We are still kind of fighting with, well, for a long time we didn't get the near real-time data as a non-meteorological compensation. I think we're now coming closer that we actually get access to the near real-time data. The reason why this was important for us because in some areas free-thaw detection is very simple, like in Siberia, where you have very drastic changes. But if you go to European conditions, you often have difficulties of explaining why backscatter changes are there. Is it because like the soil is partly frozen within your pixel? Is it because you have wet snow within the pixel? But once we have these two data chains, so the data flow from the weather forecast and the ASCAD data, I'm sure we should do a very good free-thaw product. And once we have this, it could become part of also of an HSAF data processing chain, either as part of a soil moisture product or as a standalone product. But we haven't discussed this yet or negotiated it with the HSAF team.
Okay, thank you. Just before reading this question, I would like to remind the participants about this poll that you will find in the chat. If you can give us some feedback on the poll. Some of them are open text questions, so you might have to type a sentence or two related to the event. So if you can do that, then please do it. Regina has now posted the Slido link and the code there. Thank you. And Wolfgang, back to you. Given microwave soil moisture has relative greater errors in the densely vegetated areas, how about the quality of SM rain data in those areas?
Yeah, as I said, like I'm really fascinated by the fact that SM rain seems to add by itself very little error on the data. So what we see, like if you have bad quality in the SM terrain data, it basically can be explained by bad quality in our soil moisture retrieval. And yes, the more vegetation you have, the more uncertain will also become your SM terrain rainfall estimates. Interestingly enough, if like Luca Brocker is using all the data, even for tropical forest, where obviously we don't do soil moisture. But what we kind of do in those areas, we respond to like water droplets in the canopy. That is again like like if the water droplets in the canopy, we may have an increase in backscatter of a tropical forest canopy with 1 dB or half a dB, and picking this up can kind of help to do like also an indirect estimate of precipitation. But I would rather advise not to use SM terrain in very densely forested areas, in particular like coniferous areas may be problematic. We also observe that we have problems in desert areas. Actually, the subsurface scattering, which I didn't touch today, is even a larger area of concern. So those areas where the product works the best is in areas where soil moisture works the best, which is in grassland type of areas, agricultural areas. So this is where the product quality overall is the best.
Okay. Thanks, Wolfgang. I think there's one more question. Do you have views on the planned ESA biomass P-band radar mission with respect to your work?
Not yet. Of course, I'm closely following this work because also from the ESA side, Klaus Kipperl is the science lead, and he's a close colleague of mine. So I closely follow that work, but we have not yet considered combining with ASCAT. It's a very different frequency, so I'm sure that yeah, data will not be easily comparable.
Thank you. Interesting questions. So yeah, you have interesting presentation applications. One question about estimating rainfall by soil moisture. In the graphs you showed, rainfall peaks are sometimes underestimated by the satellite. Is this because during peak rainfall, maximum soil moisture is reached and the rest is outflow to rivers or deeper groundwater?
Yeah, very good observation. This is correct. So SM terrain has two weaknesses. The first weakness is essentially it's we look into changes of soil moisture. So as our soil moisture estimates are noisy, looking into a change of a noisy estimate can give you noise in the rainfall estimate. So even, for example, if there's no rainfall and we still see like fluctuations of the soil moisture signals, they can turn into wrong precipitation estimates that are not there. And the second problem is that you highlight if the soil is already like saturated, soil moisture cannot go up even more. So in those cases, we go into saturation, and that's why we have underestimation of larger rainfall amounts. So in this case, you basically it works most reliable in the intermediate ranges of rainfall. And again, initially I would also have like been worried that the errors can become very large. And the surprising fact is, if you compare it with different other rainfall data products, that the quality often matches extremely well. And in some areas where the gauge mesh network is poor, that is one of the best products you can find. Like, for example, in some African areas.
Okay, I think that's it, Wolfgang. You've all answered all the questions, and then I think we can also. I have to thank everyone. What's that? There's one more. Is it possible to estimate rainfall if the soil is too much wet?
Yeah, this is exactly what the other question is. So
yes,
good
the saturation. Yeah.
Saturation problem.
Thanks. Okay, I think that question is for Ad tomorrow, and yes, I think Stephanie has probably answered the last question. Okay, thank you very much, Wolfgang. Thanks for your presentation, and thanks everyone for your participation today. I hope you all enjoyed it and got excited about scatterometer, both level 1B product and the soil moisture product. Tomorrow we will meet again at the same time like today. That's 1400 CEST. That's the time here in Europe, most of Europe, let's say. And yeah, please, yeah, we will make available the recordings of today's presentations and the discussions that followed, as well as the Q&A. We will try to to export it into a nicer format that can be shared with everyone. And please, please go to the polls offline if you want, and then that will be a good help for us, because like I said before, we are planning to do more of this in the future. If this is the state that we are in now, in the present scenario, we might do better, and we plan to do better than plan to make ourselves better every time, right? So thank you very much, Wolfgang and Stephanie, for the presentation today. Thanks, Regina and Stefan. Thanks for your support. We will see you tomorrow at the same time. Thanks, everyone.
Thank you.
Bye-bye.
Goodbye.
Bye.
Bye-bye.
Thank you. Bye.